Hello, and welcome to the Drowsy Professor. I'm so glad you found your way here tonight, to this quiet corner of the world where we explore the gentle mysteries of our planet's deep past. As you settle in, wherever you are, perhaps curled up in bed with soft blankets pulled close, or nestled in a favorite chair as the day slowly fades, let me know where in the world and at what time you're watching. There's something wonderfully comforting about knowing we're sharing this peaceful moment together, even across the distances that separate us. Now, take a moment to get truly comfortable. Adjust your pillows, let your shoulders drop just a little, and take a slow, deep breath. Feel the air fill your lungs gently, then release it with a soft sigh. Tonight, we're going to journey together to a time so distant it feels almost like a dream. Nearly 450 million years ago, when our planet wore a completely different face and the seas held stories we're only just beginning to understand. We'll be exploring one of Earth's great transformations, a time when the oceans themselves began to change in ways both subtle and profound. But don't worry about remembering every detail or following every scientific term. This isn't a test, and there's no need to stay alert or take notes. Instead, think of this as a gentle drift through time, where you can let the words wash over you like soft waves, carrying you toward rest while painting pictures of ancient worlds in your mind. Let your breathing slow naturally as we begin, and know that whether you listen to every word or simply let the sound of the story guide you towards sleep, you're exactly where you need to be. Imagine, if you will, that you could step through a doorway in time, leaving behind the familiar world of today and emerging into an Earth so different it might feel like visiting another planet entirely. The air would taste different on your tongue, perhaps a little saltier, a little warmer. The sky above might seem a touch more hazy, painted in shades you've never quite seen before. And beneath your feet, instead of solid ground, you'd find yourself floating gently in waters that stretch to every horizon, warm and clear and teeming with life unlike anything in our modern oceans. This is the world we're visiting tonight, the Earth of 450 million years ago, during what scientists have come to call the Late Ordovician period. It's a name that might sound formal and distant, but think of it simply as a chapter in our planet's long, slow story, a time when the rules that govern life and landscape were written in entirely different ink. In this ancient world, there are no flowers blooming on distant shores, because flowers haven't been invented yet. There are no birds singing in the morning air, no butterflies dancing through meadows, no familiar forests whispering in the breeze. Instead, the land lies mostly bare and quiet, painted in subtle shades of rock and primitive moss, while all the drama and beauty of life plays out beneath the surface of the sea. And what seas they are! Imagine floating here in these ancient waters, suspended in liquid warmth that holds you like the gentlest embrace. The water around you is crystal clear, so transparent that when you look down, you can see for what seems like miles into the depths below. Schools of creatures drift past you in the blue, some familiar in their basic shapes, like ghostly jellyfish pulsing with slow, hypnotic rhythms. Others so strange and wonderful they seem like living sculptures carved from pearl and silver. These are the trilobites, perhaps the most famous residents of this ancient world. Though if you met one drifting past you in these waters, you might think it was some sort of elaborate living jewel. Picture a creature about the size of your hand, its body segmented like a delicate chain of armor, each piece fitting perfectly with the next. Its shell catches the filtered sunlight streaming down from above, reflecting it back in subtle rainbows. Large compound eyes, some of the first complex eyes ever to evolve on our planet, peer out from its head like black pearls, taking in a world that's both alien and achingly beautiful. But the trilobites are just one note in this underwater symphony. Floating beside you, you might see the graceful forms of sea lilies. Though they're animals, not plants, despite their name. They look like underwater flowers, swaying in a breeze that doesn't exist, their feathery arms reaching upward to catch tiny particles of food drifting down from the surface. Some are tall as trees, creating underwater forests that stretch as far as the eye can see, their stems flexible and strong, bending and swaying with the gentle currents. In the deeper waters around you, other shapes move with purposes you can only guess at. There are the nautiloids, distant ancestors of today's squid and octopus, but housed in shells that spiral like architectural marvels. Some of these shells are small enough to hold in your palm, while others grow to sizes that would dwarf a person. Gentle giants of the ancient seas, propelling themselves through the water with quiet grace, their tentacles trailing behind like silk ribbons. The brachiopods carpet the seafloor below you in vast communities, their shells opening and closing in slow, rhythmic patterns as they filter feed. From a distance, they look like a field of flowers blooming on the ocean floor, each one a small miracle of efficiency and design, perfectly adapted to this underwater world that has no equivalent in our modern oceans. And everywhere, in every direction you look, there is abundance. Not the frantic, desperate abundance of competition and struggle, but something that feels more like a gentle festival of life, where every creature has found its place and purpose in the great underwater dance. The water itself seems alive with microscopic organisms, tiny plankton that drift like underwater snow, catching the light and creating a soft, dreamy glow that makes everything seem to shimmer slightly, as if you're seeing the world through the gentlest of filters. This is a world operating on a different timescale entirely from our own, where we measure our lives in decades. These creatures measure theirs in the slow accumulation of shell growth, the gradual drift from one feeding ground to another, the patient rhythm of tides and seasons that stretch across centuries. There's something deeply peaceful about this pace, something that seems to slow your own heartbeat as you float here among them. The temperature of the water around you is perfectly comfortable, like a warm bath that never grows cold. These ancient seas are much warmer than our modern oceans, heated by a sun that seems to shine with a gentler light, and warmed by atmospheric conditions that wrap the entire planet in a soft, tropical embrace. There are no ice caps at the poles, no frozen continents to chill the waters. Instead, warmth flows freely from equator to pole, creating a world where even the most distant seas feel welcoming and alive. The continents themselves are arranged differently in this ancient world, scattered across the globe in patterns that would seem strange to modern eyes. Most of the land masses are clustered around the southern hemisphere, leaving vast expanses of open ocean that stretch unbroken for thousands of miles. These great oceanic highways allow currents to flow freely around the planet, mixing nutrients and warmth in endless cycles, creating conditions that support life in ways our modern, more fragmented oceans cannot quite match. If you could rise to the surface of these ancient waters and look out toward the horizons, you'd see islands and continents that exist nowhere in our modern world. Gondwana, a massive southern supercontinent, dominates the southern hemisphere, while smaller landmasses drift slowly northward like lazy swimmers in an endless pool. The shapes of these ancient lands would seem both familiar and foreign, recognizable as continents, but arranged in patterns that remind you just how far you've traveled through time. But it's not just the arrangement of the continents that makes this world feel different. The very chemistry of the oceans has its own unique signature. These waters are rich in minerals and nutrients that have been dissolved from rocks and carried by rivers over millions of years. The calcium carbonate that forms the shells of so many creatures is abundant here, creating conditions perfect for the growth of the elaborate skeletal structures that house the sea life around you. The oxygen levels in these waters are different too, creating an atmosphere that might make you feel slightly lightheaded, as if you're standing at high altitude where the air is thin and clean. This isn't the oxygen-rich atmosphere of our modern world, but something more delicate, more carefully balanced, supporting life forms that have evolved to thrive in these specific conditions. As you float here in this ancient ocean, suspended between the warm surface and the mysterious depths below, you begin to understand that you're witnessing something incredibly special. A moment in Earth's history when the conditions for life were aligned in ways that created abundance almost beyond imagination. This is life before the great experiments of evolution had scattered organisms into every possible niche, before the competition for resources had grown fierce and complex. Instead, this feels like life in its adolescence, growing strong and diverse, but not yet pressed into the desperate creativity that would come later. The sounds of this underwater world are different too, if you know how to listen. There's the gentle whisper of currents moving through underwater forests, the soft clicking and scraping of shells against the seafloor, the distant songs of creatures whose voices we've never heard and never will. It's a soundscape that exists nowhere in our modern world, an audio signature of abundance and peace that seems to slow time itself. And perhaps most remarkably, this is a world in balance. The creatures around you exist in relationships that have been refined over millions of years of gradual change. The predators are present, but not dominant. The prey species abundant, but not overwhelming their environment. It's as if life has found a kind of equilibrium that our modern, rapidly changing world rarely achieves, a steady state where change happens slowly enough for adaptation to keep pace. But even as you float here in this perfect moment, suspended in warm water among creatures that seem to have achieved a kind of timeless harmony, there are already subtle signs that change is coming. Nothing dramatic or sudden. This ancient world doesn't work that way. Instead, there are gentle shifts in the currents, almost imperceptible changes in the temperature, tiny variations in the chemistry of the water that only the most sensitive instruments could detect. These changes are so gradual, so gentle, that the creatures around you continue their ancient routines without concern. The trilobites still hunt for food along the seafloor, their compound eyes scanning for the small prey that sustains them. The sea lilies still wave their feathery arms in the currents, filtering nutrition from the water with patient efficiency. The great nautiloids still patrol their territories with the confidence of creatures that have ruled these seas for millions of years. Yet change is indeed coming to this ancient world, change that will transform everything you see around you, not through violence or catastrophe, but through the same kind of gradual, inexorable process that created this abundance in the first place. The Earth itself is beginning to shift and adjust, responding to forces as vast and slow as the orbit of the planet around the Sun, as subtle as the slow drift of continents across the face of the globe. These are the kinds of changes that happen on timescales that dwarf human experience. Changes measured not in years or decades, but in hundreds of thousands of years, in millions of years. From the perspective of a single trilobite or sea lily, these changes are so slow as to be invisible, like watching a mountain grow or a canyon form. But from a perspective of deep time, from the viewpoint of geological patience, these changes represent one of the most significant transformations in the history of life on Earth. As you float here in these ancient waters, surrounded by abundance and peace, you're witnessing the last golden moments of one of Earth's great ages, a time when the seas were warm and welcoming and full of life that would soon face its greatest test. The creatures around you don't know what's coming, can't know what's coming, because they exist in the eternal present that characterizes all life before human consciousness began to worry about the future. And perhaps that's as it should be. Perhaps there's wisdom in this ancient approach to existence, this focus on the immediate moment, the current meal, the warm water that surrounds and supports and sustains. As you begin to let yourself sink deeper into the peace of this ancient world, you might find that their approach to time, patient, present, unworried about distant futures, begins to seep into your own awareness, slowing your heartbeat, softening your breathing, reminding you that in this moment, right now, you too are floating safely, surrounded by warmth and support, free to simply be. The ancient seas stretch endlessly around you, warm and welcoming and full of gentle life. And for now, that's all you need to know. The changes that are coming will unfold in their own time, at their own pace, following laws as gentle and inexorable as gravity itself. But that's a story for the next part of our journey together. For now, let yourself float peacefully in these ancient waters, among creatures that knew how to live in harmony with their world, and feel the timeless peace that comes from understanding your place in the vast, slow story of our planet's long and beautiful history. To truly understand the gentle transformation that would eventually reshape these ancient seas, we need to spend more time here in this golden age, floating peacefully among creatures that have no knowledge of the changes to come. Think of this as settling into a comfortable chair in a vast library, opening a book about a world so different from our own that it feels like pure imagination. Yet every word is true, every detail verified by the patient work of scientists who have learned to read stories written in stone. The world you're drifting through right now represents one of life's great success stories, a time when evolution had been experimenting with different forms and strategies for nearly 100 million years since complex life first appeared in the fossil record. By the time of the Late Ordovician, the seas had become crowded with an astonishing diversity of life forms, each perfectly adapted to its particular niche in the underwater ecosystem that stretched across the globe. Let your breathing slow as we explore this world together, imagining yourself as a patient observer drifting through these ancient waters, watching the daily dramas of creatures whose lives were measured in rhythms completely different from our own. Time moves differently here, more like the slow accumulation of sediment on the seafloor than the frantic pace of modern life. Each moment stretches out like honey, sweet and golden and unhurried. The trilobites, those remarkable arthropods that dominated these ancient seas, had by this time evolved into an astounding variety of forms. Some were tiny, no bigger than a button, perfectly adapted for life in the spaces between grains of sand on the seafloor. Others had grown to impressive sizes, their segmented bodies armored like medieval knights, patrolling territories that might span several square miles of ocean bottom. As you float above them, watching their slow, methodical movements across the sediment, you can almost sense the ancient wisdom encoded in their simple behaviors, strategies refined over millions of years of successful living. Picture one of these larger trilobites making its way across the seafloor below you. Its movement is unhurried, almost meditative, as it uses specialized limbs to sift through the soft sediment, searching for the small organisms that make up its diet. There's something deeply peaceful about watching this process, this patient search for sustenance that has no urgency, no anxiety. The trilobite simply moves forward, one segment at a time, leaving a gentle trail in the sediment behind it like a signature written in an ancient language. The compound eyes of these creatures represent one of evolution's early masterpieces of engineering. Each eye is made up of hundreds of individual lenses, creating a vision system that can detect the slightest movement in the water around them. But rather than creating a frantic awareness of potential threats, these eyes seem to provide a kind of calm omniscience, allowing the trilobite to be aware of its surroundings without being overwhelmed by them. It's a lesson in mindfulness that our modern world could learn from. Surrounding these trilobites, the seafloor communities stretch out in all directions like underwater cities, but cities designed by some benevolent architect who understood that abundance and beauty could coexist. The brachiopods cluster together in vast beds, their shells creating a living carpet that shifts and shimmers as millions of individual organisms open and close their shells in response to the subtle currents flowing through the water. Each brachiopod is a marvel of biological engineering, its two shells perfectly hinged to create a chamber where specialized organs can filter tiny particles of food from the water. The process is so efficient, so perfectly adapted to the conditions of these ancient seas, that entire communities of these creatures can thrive in areas where modern marine life would struggle to find enough nutrition. They've learned to live together in harmony, each individual contributing to the health of the whole community through its simple act of feeding. Rising from this living carpet, the crinoids create underwater forests that dwarf anything in our modern oceans. These sea lilies, despite their plant-like appearance, are actually animals, echinoderms related to modern starfish and sea urchins. But where their modern relatives are typically small and hidden in tide pools or along rocky shores, these ancient cousins grew to magnificent sizes, their stems reaching heights of 10, 20, even 30 feet above the seafloor. Imagine drifting through one of these crinoid forests, your body gently bumping against the flexible stems as they sway in the current. Each stem is made up of hundreds of individual disc-shaped segments, fitted together like a stack of coins, creating a structure that's both strong and flexible. At the top of each stem, a crown of feathery arms waves gracefully in the water, creating patterns that are both hypnotic and beautiful to watch. These arms are covered with tiny grooves lined with even tinier hairs that beat in coordinated waves, creating currents that draw food particles toward the creature's mouth. It's a feeding strategy of incredible elegance and efficiency, allowing these creatures to harvest nutrition from the water column without expending much energy in the process. Watching them feed is like watching a slow-motion dance performed by dozens of graceful arms, each movement perfectly timed and coordinated. The water around these crinoid forests is often filled with a gentle snow of marine particles, tiny organisms, and bits of organic matter that drift down from the surface waters above. This marine snow provides the foundation for the entire ecosystem, carrying nutrients from the sunlit surface waters down to the communities of filter feeders that carpet the deeper seafloor. It's a system of incredible efficiency, where nothing is wasted and every particle of nutrition is captured and utilized by some organism perfectly adapted to that particular role. Moving through these underwater forests, you begin to understand that you're witnessing an ecosystem that operates on principles of cooperation and efficiency rather than competition and conflict. While predators certainly exist in these ancient seas, they're not the dominant force that they would become in later evolutionary periods. Instead, this is a world where most creatures have learned to make their living by working with the natural flows of energy and nutrients that circulate through the ocean systems. The nautiloids that cruise through these waters represent perhaps the most sophisticated predators of this ancient world, but even they seem to hunt with a kind of unhurried dignity. These creatures, encased in shells that spiral in perfect mathematical curves, propel themselves through the water using a form of jet propulsion that's both elegant and efficient. Watching one of these ancient nautiloids navigate through a crinoid forest is like watching a master craftsman at work. Every movement precise and purposeful, but never rushed or desperate. The shells of these nautiloids are engineering marvels in their own right, divided into chambers that allow the creature to control its buoyancy with remarkable precision. By adjusting the amount of gas and liquid in these chambers, a nautiloid can rise or sink through the water column at will, maintaining perfect neutral buoyancy as it searches for prey or simply explores its underwater domain. The largest of these shells can grow to sizes that would dwarf a modern dinner table, creating mobile homes for creatures that were among the most sophisticated predators the world had yet seen. But even these apex predators seem to exist in harmony with their environment rather than dominating it. Their hunting strategies are patient and methodical, more like a chess master planning several moves ahead than a modern predator driven by immediate hunger. They might spend hours or even days stalking a particular prey item, moving slowly through the water with the confidence of creatures that know their place in the world and have no need to hurry. The smaller creatures that share these ancient seas have evolved equally sophisticated strategies for survival, but their approaches tend toward cooperation and mutual benefit rather than competition and conflict. Bryozoans, tiny colonial animals, create elaborate reef-like structures that provide shelter and feeding opportunities for dozens of other species. These reefs grow slowly over decades or centuries, each generation of bryozoans building upon the work of their predecessors to create structures of remarkable complexity and beauty. Swimming through the water column above these seafloor communities, you encounter creatures that seem to exist in a state of perpetual gentle motion. Graptolites, colonial organisms that look like tiny saw blades made of organic material, drift through the water in vast swarms, their synchronized movements creating patterns that are both beautiful and mysterious. Each individual graptolite is connected to its neighbors by fine organic threads, creating colonial organisms that can stretch for yards through the water. These graptolite colonies represent one of evolution's early experiments with collective intelligence, where individual organisms coordinate their movements and behaviors to benefit the colony as a whole. Watching them move through the water is like watching a living constellation, each point of light connected to every other in a pattern that seems to pulse with its own internal rhythm. The chemistry of these ancient oceans is different from anything in our modern world, creating conditions that support forms of life that could never exist today. The water is supersaturated with dissolved minerals, particularly calcium carbonate, creating conditions where shell-building organisms can construct elaborate skeletal structures with an ease that modern marine life can only dream of. This abundance of building materials has allowed creatures to experiment with architectural forms that push the boundaries of what seems possible in biological engineering. Some of the coral-like organisms in these ancient seas build structures that rival modern cities in their complexity and scale. Stromatoporoid reefs stretch for miles across the seafloor, their layered growth patterns creating maze-like structures that provide shelter and feeding opportunities for thousands of other species. These reefs grow slowly, adding layer upon layer over centuries, creating vertical relief on the seafloor that rises like underwater mountains from the surrounding plains. The temperature of these ancient oceans is remarkably stable and warm, heated by a combination of atmospheric conditions and ocean circulation patterns that no longer exist in our modern world. There are no polar ice caps to chill the waters, no frozen continents to disrupt the global circulation of heat and nutrients. Instead, warm tropical conditions extend almost to the poles, creating a global ocean system that's like a vast, warm bath extending around the entire planet. This warmth supports metabolic rates that allow creatures to grow to sizes that would be impossible in cooler waters. Giant nautiloids cruise these seas with shells that can reach lengths of 15 feet or more. Their massive size, supported by the warm, nutrient-rich waters that provide abundant food and perfect conditions for shell growth. Imagine encountering one of these giants as it moves slowly through the water, its tentacles trailing behind like silk ribbons, its ancient eyes reflecting an intelligence that's both alien and familiar. The seasonal cycles in these ancient oceans are gentler and more predictable than anything in our modern world. Without the extreme temperature variations created by polar ice caps, the annual cycles of plankton blooms and nutrient cycling follow patterns that are both regular and sustainable. This predictability allows creatures to develop life strategies that are based on long-term stability rather than the need to adapt quickly to changing conditions. The deep waters of these ancient oceans are also different from their modern counterparts, rich in dissolved oxygen and nutrients that support life at depths where modern oceans become barren and lifeless. This oxygenation extends all the way to the deepest trenches, creating conditions where complex life can thrive even in the most remote parts of the ocean system. It's as if the entire ocean, from surface to seafloor, is one vast, interconnected living system where every drop of water can support life. As you drift through these ancient waters, suspended between the warm surface and the life-rich depths, you begin to understand that you're witnessing something that represents a peak in Earth's history, a time when conditions align to create abundance and diversity on a scale that the planet has never achieved again. This is life before the great winnowing events that would reshape evolution, before the competitive pressures that would drive organisms into increasingly specialized niches. The sounds of this underwater world create a symphony unlike anything in our modern oceans. The gentle scraping of shells against the seafloor, the whisper of currents through crinoid forests, the distant calls of creatures whose voices have been silent for hundreds of millions of years. It's a soundscape that speaks of abundance and peace, of a world where life has found its rhythm and settled into patterns that could continue unchanged for millions of years. But even as you float here in this perfect moment, surrounded by abundance and bathed in warm, life-giving water, the seeds of change are already being sown, not through any dramatic event or sudden catastrophe, but through the same slow, patient processes that created this abundance in the first place. The Earth itself is beginning to shift and adjust, responding to astronomical cycles that operate on timescales so vast they make even geological time seem hurried. These changes are so gradual, so gentle, that they're invisible to the creatures around you. The trilobites continue their patient search for food. The crinoids continue their graceful dance in the currents. The nautiloids continue their dignified patrol of ancient territories. From their perspective, the world is as stable and eternal as it has always been, a place where the rules of existence are written in stone and the abundance of life seems to stretch into an infinite future. And perhaps, in this moment, that's the most important lesson these ancient seas have to teach us. That stability and abundance are possible. That life can find ways to exist in harmony with its environment. That the frantic pace of change that characterizes our modern world is not the only way existence can unfold. As you let yourself sink deeper into the peace of these ancient waters, surrounded by creatures that knew how to live in balance with their world, you might find that their approach to time and existence begins to influence your own breathing, your own heartbeat, your own relationship with the present moment. Sometimes the most profound changes begin not with a thunderclap or a sudden shift, but with whispers so quiet they can barely be heard above the gentle rhythm of everyday life. In these ancient seas where you float, suspended in warm water among creatures that have known nothing but abundance for millions of years, the first signs of transformation are beginning to make themselves known in ways so subtle that only the most sensitive observers might notice them. Think of it like lying in bed on a peaceful night, so comfortable and relaxed that you're barely aware of your surroundings, when gradually you become conscious of a change in the air outside your window. Not a storm, nothing dramatic or alarming, but perhaps the slightest shift in temperature or a barely perceptible change in the way the breeze moves through the trees. The change is so gentle that it doesn't disturb your rest, but somewhere deep in your awareness, you register that something is beginning to shift. This is how change comes to the Ordovician seas, not as a dramatic event, but as a series of whispers that begin to accumulate over time spans so vast that individual creatures never notice them within the scope of their own lives. The trilobites continue their patient foraging across the seafloor. The crinoids continue their graceful dance in the currents. The nautiloids continue their dignified hunting expeditions through underwater forests that seem as eternal as mountains. But if you could somehow step outside the normal flow of time, if you could observe these ancient waters from the perspective of deep geological patience, you would begin to see patterns emerging that speak of changes so gradual they unfold like the growth of crystals in a cave, beautiful and inexorable and utterly without haste. The first whispers of change begin in places so distant from these warm seas that their effects take thousands of years to travel through the complex systems that govern ocean circulation and climate. Far to the south, in regions that will one day become parts of Africa and South America, the massive continent of Gondwana is beginning to drift slowly toward the South Pole, moving at a pace so glacial that it would be invisible to human observation, yet significant enough to begin shifting the fundamental patterns of global climate. This continental drift happens with all the urgency of a mountain growing or a canyon forming. Movements measured in centimeters per year, changes so slow that they're detectable only through the patient accumulation of geological evidence. But even these imperceptible movements begin to have effects that ripple outward through the interconnected systems of ocean and atmosphere, creating changes that, while still invisible to the creatures of the ancient seas, represent the first notes in a symphony of transformation that will reshape the world. As Gondwana drifts toward higher latitudes, the patterns of solar heating that have maintained the stable, warm conditions of the Ordovician seas begin to shift in ways so subtle they might be compared to the way a room gradually cools when a window is opened just a crack in another part of the house. The change is so gradual that it's barely perceptible, but over time, its effects accumulate and spread through the complex networks that connect every part of the global climate system. The ocean currents that have carried warm water from the equatorial regions toward the poles begin to encounter new patterns of heating and cooling. Where once these currents flowed unimpeded around the globe, carrying tropical warmth to even the most distant seas, they now begin to encounter subtle obstacles and redirections as the changing position of continents alters the pathways through which they flow. Imagine these ocean currents as vast rivers of warm water flowing through the sea, carrying not just heat, but nutrients and dissolved gases that support the abundant life of the Ordovician oceans. These currents have been flowing in the same basic patterns for millions of years, creating the stable conditions that have allowed complex ecosystems to develop and thrive. But now, as the continents shift position with geological slowness, these currents begin to encounter new configurations of land and sea that subtly alter their paths. The changes are so gradual that they're imperceptible within the lifetime of any individual organism. A trilobite born at the beginning of this process would live its entire life and die without ever noticing any difference in the temperature or chemistry of the water around it. Generations of crinoids would grow and reproduce and add their skeletal remains to the growing reefs without experiencing any obvious change in the conditions that support their filter-feeding lifestyle. Yet the changes are real and accumulating. In the deep ocean basins, far below the warm surface waters where most life flourishes, the patterns of water circulation are beginning to shift in response to the changing geography of the planet. Deep, cold currents that have flowed along the ocean floor for millions of years begin to encounter new obstacles and redirections as the continental masses rearrange themselves on the face of the globe. These deep ocean changes are particularly subtle because they occur in regions far removed from the abundant life of the surface waters and shallow seas. It's as if changes were beginning in the basement of a house, while the occupants of the upper floors continued their daily routines, completely unaware of the shifts taking place below them. The effects of these deep ocean changes will take thousands of years to work their way up through the water column to influence the surface conditions where most marine life exists. But influence them they will, through processes so gradual and interconnected that they represent one of the most elegant examples of how small changes can accumulate over time to create profound transformations. The deep ocean currents help regulate the temperature and chemistry of all the world's waters, carrying dissolved gases and nutrients through complex cycles that support life throughout the marine ecosystem. As these circulation patterns begin to shift, they start to alter the delicate balance of nutrients and dissolved gases that has supported the extraordinary abundance of Ordovician marine life. The changes are measured in parts per million, in temperature variations of fractions of degrees, in alterations of current patterns that shift by mere kilometers over thousands of years. Yet these tiny changes, accumulating over vast time spans, begin to create new conditions in the ancient seas. The chemistry of the oceans, which has remained remarkably stable for millions of years, begins to show the first subtle signs of change. The concentration of dissolved oxygen, which has allowed complex life to thrive even in the deepest waters, begins to fluctuate in ways so slight they would be undetectable to any measurement instrument available to ancient organisms. Yet these fluctuations, invisible though they are, represent the beginning of a process that will eventually reshape the entire marine ecosystem. The calcium carbonate saturation that has made it so easy for shell-building organisms to construct their elaborate skeletal structures also begins to show the first signs of variation. The supersaturated conditions that have allowed creatures to experiment with architectural forms of incredible complexity begin to fluctuate in response to changes in ocean circulation and atmospheric chemistry. Again, the changes are so gradual that no individual organism experiences them as stress or difficulty, but they represent the beginning of a shift toward conditions that will eventually favor different survival strategies. Perhaps most significantly, the global temperature patterns that have maintained tropical or subtropical conditions almost to the poles begin to show the first subtle signs of change. The temperature variations are tiny, measured in fractions of degrees over thousands of years, but they represent the beginning of a process that will eventually lead to the formation of ice at the poles for the first time in millions of years. This polar cooling begins as the slightest whisper of change, so gradual that it's detectable only through the most sensitive measurements. It starts in the highest latitudes, in regions so remote from the warm equatorial seas that its effects take thousands of years to propagate through the global climate system. But even these distant changes begin to alter the fundamental dynamics that have maintained the stable, warm conditions of the Ordovician world. The formation of ice at the poles is still thousands of years in the future, but the conditions that will eventually make it possible are beginning to develop through processes so gradual they're almost like geological breathing. Vast, slow cycles of cooling and warming that operate on timescales that dwarf human experience. The first ice that forms will be temporary, melting and reforming with seasonal cycles. But even these temporary changes begin to alter the global patterns of heat and moisture circulation. As small amounts of water begin to freeze at the poles, even temporarily, they remove that water from the global circulation system in ways that have cascading effects throughout the ocean. Water that was once part of the global cycle of evaporation, precipitation, and circulation becomes locked, even briefly, in ice, reducing the overall volume of water in the system and beginning to alter sea levels in ways so gradual they're imperceptible to marine life, but significant to the geological processes that shape coastlines and ocean basins. These sea level changes begin as variations measured in millimeters over thousands of years, shifts so subtle that they would be undetectable to creatures whose lives are measured in years or decades rather than geological ages. Yet these tiny changes in sea level begin to alter the depth and extent of the shallow seas, where most Ordovician life flourishes, creating the first whispers of change in the underwater landscapes that have remained stable for millions of years. The coral-like organisms and reef-building communities that have created vast underwater cities across the shallow seas begin to experience conditions that are subtly different from those their ancestors knew. The changes are so gradual that they don't represent stress or challenge, but rather a slow shift toward environmental conditions that will eventually favor different architectural strategies and different approaches to reef construction. The plankton communities that form the foundation of the marine food web also begin to experience the first subtle effects of these changing conditions. The microscopic organisms that drift through the surface waters, turning sunlight and dissolved nutrients into the biological energy that supports all marine life, encounter water chemistry and temperature conditions that are shifting so slowly they represent evolutionary opportunity rather than crisis. These planktonic communities respond to changing conditions in ways that are barely perceptible, but represent the beginning of evolutionary adaptations that will eventually reshape the entire marine ecosystem. New species begin to evolve that are better adapted to the slightly different conditions, while existing species begin to shift their ranges and behaviors in response to subtle changes in temperature, chemistry, and nutrient availability. The filter-feeding communities that dominate the seafloor also begin to experience the first whispers of change as the rain of marine snow from the surface waters begins to shift in composition and timing. The seasonal cycles of plankton blooms and nutrient cycling, which have followed predictable patterns for millions of years, begin to show subtle variations that will eventually accumulate into significantly different environmental conditions. Even the great nautiloids, apex predators of the ancient seas, begin to encounter conditions that are subtly different from those their ancestors knew. The prey species they depend on begin to show shifts in distribution and abundance that are too gradual to affect hunting success, but represent the beginning of changes that will eventually require new hunting strategies and new approaches to predation. All of these changes unfold with the patience of geological time, creating shifts so gradual that they're invisible to individual organisms, but significant when viewed from the perspective of deep time. It's as if the ancient seas are undergoing a transformation as slow and gentle as the changing of seasons, but stretched across thousands of centuries rather than a single year. As you float in these ancient waters, suspended between the warm surface and the mysterious depths, you're witnessing the very beginning of one of Earth's great transformations. The creatures around you continue their ancient routines, unaware that the conditions supporting their abundance are beginning to shift in ways that will eventually reshape the entire marine world. There's something both poignant and peaceful about this moment. This last golden time before change becomes noticeable, when the ancient harmony of these seas still seems as eternal as the stars. The whispers of transformation are growing slightly stronger now, but they're still so subtle that they enhance rather than disturb the peace of these ancient waters. Like the sound of distant rain that makes a quiet evening even more comfortable. These first signs of change add a depth and complexity to the ancient seas that makes them even more beautiful and mysterious than before. There's something almost musical about the way change moves through the ocean systems of our planet, like a vast, slow symphony played on instruments made of water and wind, ice and stone. As you continue to float in these ancient seas, suspended in warmth that has embraced this world for millions of years, you're about to witness the next movement in this geological symphony. The gradual cooling that will transform these tropical waters into something entirely different. But even the word cooling might give the wrong impression, suggesting something sudden or dramatic. What's happening in these ancient seas is more like the way a cup of tea gradually returns to room temperature when left sitting on a table. So slowly that you might not notice the change for a very long time, yet inevitable and measurable if you have the patience to observe it over the proper time scale. The cooling begins in the most distant reaches of the Southern Ocean, where the great continent of Gondwana has been drifting slowly toward the South Pole for thousands of years. This movement happens with all the urgency of a mountain growing, so slowly that it would be invisible to human observation, yet significant enough to begin altering the fundamental patterns that have kept these ancient seas warm and welcoming for so long. Picture, if you will, the South Pole as it exists in this ancient world. Not the ice-covered wasteland we know today, but a region of open ocean warmed by currents that flow unimpeded around the globe. For millions of years, warm water has been able to circulate freely from the equator to the poles and back again, creating a planetary ocean system that maintains tropical or subtropical temperatures almost everywhere. It's like a vast central heating system for the planet, distributing warmth so efficiently that even the most distant seas remain comfortable and life-giving. But as Gondwana drifts into higher latitudes, it begins to disrupt this ancient circulation pattern in ways that are subtle at first but will eventually prove profound. The continent acts like a massive dam slowly moving into position across the global ocean currents, forcing them to find new pathways and creating conditions where, for the first time in millions of years, water in the polar regions begins to lose heat faster than it can be replaced by warm currents from the equator. This process unfolds with the patience of geological time, so slowly that it would be undetectable to any organism living through it. The temperature changes begin as variations so small they would require the most sensitive modern instruments to measure, fractions of degrees spread across thousands of years. Yet these tiny changes, accumulating year after year, century after century, begin to create conditions unlike anything this planet has experienced since complex life first flourished in its oceans. The first ice that forms in these polar regions is nothing like the massive ice sheets we know from more recent geological periods. Instead, it appears as thin, seasonal formations that freeze during the coldest parts of a year and melt again as temperatures warm. Think of it like frost forming on a window on a cold morning, delicate and temporary, yet significant because it represents the crossing of a threshold that hasn't been crossed for millions of years. But even this temporary ice begins to have effects that ripple outward through the interconnected systems of ocean and atmosphere. When water freezes, even briefly, it removes fresh water from the ocean system, leaving behind water that's slightly more saline, slightly denser, slightly different in its chemical properties. This denser water begins to sink toward the ocean floor, creating new patterns of circulation that will eventually affect marine ecosystems thousands of miles away from the polar regions where the ice forms. These circulation changes happen so gradually that they're like watching the hands of a clock move, imperceptible in the moment, but significant when viewed over longer time periods. Deep ocean currents that have flowed in the same basic patterns for millions of years begin to encounter new conditions as cold, dense water from the polar regions starts to flow along the ocean floor toward the equator, carrying with it chemical signatures and temperature characteristics that are different from anything these ancient seas have known. As you float in these warm waters, still comfortably suspended among crinoid forests and trilobite communities that continue their ancient routines, you're beginning to experience the first subtle effects of these distant changes. The water around you is still warm and welcoming, still rich with the nutrients and dissolved gases that support abundant life, but sensitive instruments might detect the slightest variations in temperature and chemistry that speak of transformations occurring in the deep ocean circulation patterns. The cooling process accelerates, though acceleration in geological terms still means changes that unfold over thousands and tens of thousands of years. As more ice forms at the poles, more fresh water is removed from the global ocean system, causing sea levels to drop in ways that are initially almost imperceptible but gradually become more significant. The shallow seas where you float, which have covered vast areas of the continents for millions of years, begin to experience their first retreat in living memory. This sea level drop happens like the slow draining of a bathtub, so gradually that the marine communities have time to adjust and migrate to deeper areas as their shallow water habitats slowly disappear. There's no catastrophe here, no sudden crisis, just the gentle pressure of changing conditions that require adaptations and adjustments from the communities that have made these shallow seas their home for millions of years. The coral-like organisms and reef-building communities that have created underwater cities across these shallow seas begin to experience conditions they've never encountered before. As water levels drop, the reefs that once thrived in comfortable depths suddenly find themselves in shallower water, exposed to more intense sunlight and more variable temperature conditions. Some reef communities begin to struggle under these new conditions, while others discover opportunities in the deeper waters that are becoming newly available as ocean circulation patterns shift. The response of these reef communities to changing conditions is a masterpiece of slow adaptation. Rather than dramatic die-offs or sudden migrations, what happens is a gradual shift in species composition and reef architecture that unfolds over thousands of years. Species that are better adapted to the new conditions gradually become more common, while those that struggle under the changing circumstances slowly decline in numbers. It's evolution in action, but evolution at its most patient and gradual. The brachiopod communities that carpet vast areas of the seafloor also begin to respond to the changing conditions in ways that are subtle but significant. These filter-feeding organisms, which have thrived in the stable, nutrient-rich conditions of the Ordovician seas, encounter water chemistry and temperature conditions that require adjustments to their feeding and reproduction strategies. Some species begin to shift their ranges toward areas where conditions remain more favorable, while others begin to evolve new physiological adaptations that allow them to cope with the changing environment. The great crinoid forests, those underwater cathedrals of feathery arms and flexible stems, begin to show the first signs of response to changing ocean conditions. The seasonal cycles of plankton blooms that have provided their primary food source begin to shift slightly as changing temperature and circulation patterns alter the timing and intensity of nutrient cycling in the surface waters. The crinoids adapt to these changes with characteristic patience, adjusting their feeding behaviors and growth patterns in ways that allow them to continue thriving even as the conditions around them slowly transform. The planktonic communities that form the foundation of the marine food web undergo perhaps the most significant changes during this period of gradual cooling. These microscopic organisms, which float in the surface waters and convert sunlight and dissolve nutrients into biological energy, are highly sensitive to changes in temperature and water chemistry. As conditions begin to shift, new planktonic species begin to evolve that are better adapted to cooler water temperatures and different nutrient cycling patterns. This evolutionary response happens with surprising speed, at least by geological standards. Planktonic organisms have short generation times compared to larger marine creatures, allowing them to adapt to changing conditions within thousands rather than millions of years. As new species evolve and existing species shift their ranges, the composition of planktonic communities begins to change in ways that will eventually affect every level of the marine food web. The changes in planktonic communities create ripple effects that flow both up and down through the marine ecosystem. The marine snow that drifts down from the surface waters, carrying nutrients to the filter-feeding communities on the seafloor, begins to change in composition and timing as different planktonic species become dominant. Some filter feeders thrive under these new conditions, while others find the changing food supply challenging and begin to seek out new habitats or evolve new feeding strategies. The predatory species that hunt in the water column, including the great nautiloids that cruise through these ancient seas like living submarines, also begin to encounter changing conditions as their prey species respond to shifting planktonic communities. The abundance and distribution of prey organisms begin to show subtle variations that require adjustments to hunting strategies and territorial ranges. The nautiloids, with their sophisticated eyes and jet propulsion systems, prove remarkably adaptable to these changing conditions, shifting their hunting grounds and prey preferences with the flexibility that has made them successful predators for millions of years. The cooling process continues to accelerate as more ice forms at the poles and sea levels continue their gradual descent. The shallow epicontinental seas that have supported some of the most diverse marine communities in Earth's history begin to shrink noticeably as water that once covered vast areas of the continents flows back toward the deeper ocean basins. This retreat of the seas happens slowly enough that marine communities can migrate toward deeper water, but fast enough to begin creating significant changes in the available habitat for shallow water species. As the seas retreat, new land areas begin to emerge for the first time in millions of years. These newly exposed lands are initially barren and lifeless, covered with marine sediments that have accumulated over vast periods of time. But they represent new opportunities for the primitive land plants that are just beginning to colonize terrestrial environments during this period. The interaction between retreating seas and expanding terrestrial vegetation begins to create new patterns of weathering and erosion that will eventually affect ocean chemistry in ways that add to the ongoing changes. The cooling waters also begin to affect the great volcanic systems that have helped maintain warm global temperatures throughout the Ordovician period. As ocean circulation patterns change and atmospheric chemistry shifts in response to cooling temperatures and changing biological activity, the volcanic processes that have contributed to global warming begin to operate under different conditions. The relationship between volcanic activity and global climate is complex and operates on timescales that dwarf even geological patience. But the changes that begin during this period of cooling will eventually contribute to further climate shifts. Through all of these changes, the ancient seas maintain their essential character as warm, life-supporting environments. The cooling that's occurring is significant from a geological perspective, but it's still measured in degrees that wouldn't be immediately noticeable to a human observer. The water around you remains comfortable and welcoming, still supporting the abundant life that has characterized these seas for millions of years. The trilobites continue their patient foraging, the crinoids continue their graceful feeding, the nautiloids continue their dignified hunting expeditions. Yet the seeds of more dramatic change are being sown during this period of gradual cooling. The ice that forms at the poles, initially temporary and seasonal, begins to persist for longer periods as global temperatures continue their slow decline. The circulation patterns that have maintained global warmth for millions of years continue to be disrupted as continental positions shift and polar cooling intensifies. The delicate balance of atmospheric and oceanic chemistry that has supported unprecedented biological diversity begins to shift toward conditions that will eventually favor different forms of life. As you float here in these ancient waters, still warm and supportive but beginning to carry the subtle signatures of distant change, You're witnessing one of the most elegant examples of how our planet's systems respond to shifting conditions. The cooling that's transforming these seas happens with such grace and patience that it allows life to adapt and adjust rather than simply overwhelming it with sudden change. It's a masterclass in the art of gradual transformation, showing how even profound changes can unfold in ways that preserve continuity while enabling evolution and adaptation. The ancient seas around you continue to pulse with life and activity, but they're no longer quite the same seas they were just a few thousand years ago. They're becoming something new, something that will eventually support different communities and different forms of abundance. The transformation is as gentle as the cooling of that cup of tea, as patient as the movement of continents, as inevitable as the turning of astronomical cycles that operate on timescales vast enough to reshape worlds. In the gentle art of survival, there are no dramatic gestures, no sudden revelations, no moments of crisis that demand immediate heroic responses. Instead, life adapts through countless small adjustments, tiny modifications, and patient experiments that unfold across generations, like the slow growth of coral reefs or the gradual deepening of river valleys. As you float in these ancient waters, surrounded by creatures that have been perfecting their survival strategies for millions of years, you're about to witness one of evolution's most elegant performances, the quiet dance of adaptation that allows life to flow like water around obstacles, finding new pathways and possibilities even as familiar conditions slowly transform. The trilobites that crawl across the seafloor beneath you have become master practitioners of this gentle art of adaptation. These remarkable arthropods, with their compound eyes and segmented bodies, have already survived and thrived through dozens of smaller environmental changes during their long evolutionary history. Now, as the conditions in these ancient seas begin to shift in ways more significant than anything in recent geological memory, they respond not with panic or struggle, but with the same patient flexibility that has made them successful for over 100 million years. Some trilobite species begin to make subtle adjustments to their feeding strategies, spending more time in areas where changing ocean conditions have concentrated nutrients in new patterns. Others start to modify their burrowing behaviors, digging slightly deeper into the sediment to find the optimal conditions for growth and reproduction. These changes happen so gradually that each generation experiences only tiny variations from the lifestyle of their parents. Yet over thousands of years, these small adjustments accumulate into new survival strategies perfectly suited to the slowly changing environment. The compound eyes of these ancient creatures, those marvels of early optical engineering, begin to show subtle variations that help them adapt to changing light conditions as ocean chemistry and plankton communities shift. Some lineages develop eyes that are slightly more sensitive to different wavelengths of light, allowing them to hunt more effectively as the clarity and composition of the water around them gradually changes. Others modify the structure of their eyes to better detect the movement patterns of prey species that are themselves adapting to new conditions. Perhaps most remarkably, some trilobite species begin to experiment with new body forms that are better suited to the changing physical conditions of their environment. As sea levels slowly drop and ocean circulation patterns shift, some shallow water habitats become more turbulent, while others become more still and sediment-laden. Trilobites respond to these changing conditions by evolving body shapes that are more streamlined for swimming in turbulent water, or more specialized for efficient movement through thick sediment layers. The great crinoid forests that sway gently around you also demonstrate evolution's patient approach to environmental change. These sea lilies, despite their plant-like appearance, are animals with the ability to adjust their growth patterns, feeding behaviors, and reproductive strategies in response to changing conditions. As the planktonic communities that provide their primary food source begin to shift in composition and seasonal timing, the crinoids respond with subtle modifications to their feeding apparatus and growth cycles. Some crinoid species begin to grow their feeding arms longer and more elaborate, creating more efficient filters for capturing the changing types of marine snow that drift down from the surface waters. Others modify the timing of their reproductive cycles to better match the new seasonal patterns of food availability. Still, others begin to experiment with different growth forms, some becoming more compact and sturdy to better withstand the slightly more turbulent water conditions that result from changing circulation patterns. The flexibility of these ancient sea lilies is truly remarkable to observe. Individual crinoids can adjust their feeding behavior throughout their lifetimes, extending or retracting their arms in response to current conditions, changing their orientation to better capture food particles, even modifying their biochemistry to extract nutrition more efficiently from the gradually changing composition of marine snow. It's like watching flowers that can not only turn to follow the sun, but can also change their shape, size, and even their basic metabolic processes to better suit the conditions around them. The reef-building communities that create underwater cities across these ancient seas show perhaps the most sophisticated adaptive responses to changing conditions. These complex ecosystems, built up over millions of years through the collaborative efforts of countless organisms, begin to reorganize themselves in ways that maintain their essential functions while adjusting to new environmental realities. Coral-like organisms that have thrived in the stable, warm conditions of the Ordovician seas begin to experiment with new architectural strategies as water temperatures and chemistry slowly shift. Some species develop more robust skeletal structures that can better withstand the slightly more variable conditions they're beginning to encounter. Others begin to modify their symbiotic relationships with the microscopic organisms that help them extract nutrition from the water, creating partnerships that are better suited to the changing chemical composition of the ancient seas. The bryozoans, those tiny colonial animals that create elaborate reef-like structures, demonstrate adaptation at the community level as they begin to build colonies with different architectural patterns that are better suited to the changing flow patterns of ocean currents. Some colonies become more compact and dome-shaped to better resist turbulence, while others develop more open, branching structures that can more efficiently filter nutrients from water that's changing in density and composition. Perhaps most fascinating of all, these reef communities began to develop new forms of cooperation and resource sharing that help them maintain their productivity even as individual species face new challenges. Organisms that once competed for the same resources began to specialize in slightly different feeding strategies, creating more efficient use of available nutrients. Species that once occupied the same ecological niches began to partition their habitat more finely, allowing more species to coexist in the same space. The brachiopods that carpet vast areas of the seafloor also show remarkable adaptive flexibility as they encounter changing conditions. These filter-feeding organisms, which have specialized in extracting nutrition from the water column, begin to modify their shell architectures and feeding apparatus to better cope with changes in the composition and flow patterns of the water around them. Some brachiopod species develop shells with more elaborate ridge patterns that create more efficient water flow across their feeding organs. Others modify the internal structure of their shells to better regulate the flow of water through their feeding chambers. Still, others begin to experiment with different orientations and positioning strategies that allow them to take advantage of new patterns of current flow and nutrient distribution. The adaptive responses of these filter feeders ripple through the entire ecosystem as they modify the way nutrients and particles are processed and recycled within the marine environment. Their feeding activities help determine which types of organic matter settle to the seafloor and which remain suspended in the water column, influencing the conditions that other organisms must adapt to. The planktonic communities that drift through the surface waters above you undergo perhaps the most rapid adaptive changes during this period of environmental transition. These microscopic organisms, with their short generation times and high reproductive rates, can evolve new characteristics within thousands rather than millions of years, making them the first responders to changing ocean conditions. New planktonic species begin to appear that are better adapted to the cooler water temperatures and different nutrient cycling patterns that result from changing ocean circulation. Some of these new species develop more efficient photosynthetic apparatus that can extract energy from sunlight even in the slightly different light conditions created by changing atmospheric and water chemistry. Others evolve new biochemical pathways that allow them to thrive in water with different mineral concentrations and pH levels. The evolution of new planktonic species creates opportunities for other organisms throughout the marine ecosystem. Filter feeders develop new feeding strategies to take advantage of the different types of marine snow created by new planktonic communities. Predators modify their hunting behaviors to pursue the new types of prey that emerge from evolving planktonic ecosystems. The great nautiloids that cruise through these ancient waters like living submarines show their own forms of adaptive flexibility as they encounter changing prey distributions and environmental conditions. These sophisticated predators, with their complex eyes, jet propulsion systems, and elaborate shells, begin to modify their hunting strategies and territorial behaviors in response to the shifting patterns of abundance in their prey species. Some nautiloid lineages begin to develop shells with slightly different chamber configurations that allow them to dive deeper or remain neutrally buoyant under different pressure and temperature conditions. Others modify their tentacle arrangements and sensory systems to better detect and capture prey that has adapted new behaviors in response to changing environmental conditions. The predatory strategies of nautiloids also begin to evolve in subtle ways as they learn to hunt more effectively in the changing conditions of the ancient seas. Some species become more specialized in hunting particular types of prey that are thriving under the new conditions, while others become more generalized, developing the ability to switch between different prey species as abundances shift. Perhaps most remarkably, some nautiloid species begin to show what appears to be learned behavioral adaptations, with individuals modifying their hunting strategies based on experience with changing prey behaviors and environmental conditions. While these ancient creatures certainly don't possess the complex intelligence of modern cephalopods, they do show signs of behavioral flexibility that allows them to adjust their activities to changing circumstances within their own lifetimes. The adaptive responses occurring throughout these ancient marine ecosystems create complex feedback loops that help stabilize communities even as environmental conditions continue to change. As some species develop new feeding strategies, they create new opportunities for other species. As some organisms modify their habitat preferences, they reduce competition and allow other species to expand their ranges. As new symbiotic relationships develop, they create more efficient ways of utilizing available resources. These feedback loops operate like a vast, slow conversation between species and their environment, with each adaptation creating new possibilities and new challenges that drive further adaptation. The result is not a simple linear response to environmental change, but a complex dance of coevolution that creates new forms of stability and resilience even as fundamental conditions continue to shift. The chemical cycling within these marine ecosystems also begins to show adaptive changes as organisms modify their metabolic processes to cope with changing water chemistry. Some species develop new biochemical pathways that allow them to process nutrients more efficiently under the new conditions, while others begin to produce different types of waste products that are better suited to the changing chemical environment of the ancient seas. These metabolic adaptations have far-reaching effects throughout the ecosystem as they alter the types and concentrations of dissolved chemicals in the water. The changes in water chemistry, in turn, create new selective pressures that drive further adaptation in other species, creating cascading effects that flow through every level of the marine food web. The seasonal cycles that govern life in these ancient seas also begin to show adaptive modifications as organisms adjust their reproductive timing, feeding behaviors, and migration patterns to better match the changing patterns of temperature, light, and nutrient availability. Some species begin to reproduce earlier or later in the year to take advantage of new seasonal patterns of food abundance. Others modify their metabolic rates to better cope with changing seasonal temperature variations. These temporal adaptations are particularly important because they help maintain the synchronization between different species that have evolved interdependent relationships. As one species shifts its seasonal timing, Its partners and predators must also adjust their schedules to maintain the ecological relationships that support the entire community. Throughout all of these adaptive changes, the essential character of life in these ancient seas remains remarkably stable. The fundamental strategies that have made these marine communities successful, filter feeding, predation, reef building, planktonic photosynthesis, continue to operate even as the specific ways they're implemented undergo gradual modification. It's like watching a master musician play a familiar melody on a slightly different instrument, maintaining the essential beauty and structure of the music while adapting to new tonal possibilities. The pace of these adaptive changes matches the pace of environmental change, creating a harmonious relationship between life and environment that allows for continuous adjustment without catastrophic disruption. Each generation of organisms experiences conditions that are only slightly different from those their parents knew, allowing adaptation to proceed through the normal processes of variation and selection that have shaped life throughout its long history. As you float here among these quietly adapting communities, surrounded by creatures that are demonstrating evolution's most elegant responses to environmental change, you're witnessing one of life's most fundamental capabilities, the ability to flow like water around obstacles, finding new pathways and possibilities even as familiar landscapes slowly transform. The adaptations occurring around you happen so gradually, so gracefully, that they enhance rather than disrupt the ancient peace of these seas, creating new forms of abundance and beauty even as older forms slowly fade into geological memory. Imagine watching the tide go out on a vast beach, but stretched across not hours, but millennia, not covering miles, but continents, not affecting a single shoreline, but reshaping the very geography of an entire planet. This is the great retreat of the seas that you're about to witness. A transformation so gradual and so vast that it would be invisible to any single observer, yet so profound that it will change the fundamental character of life on Earth. As you float in these ancient waters, still warm and welcoming despite all the changes they've undergone, you're about to experience one of geology's most patient and elegant performances. The retreat begins almost imperceptibly, like the way morning mist gradually lifts from a lake, so slowly that you don't notice it happening until you suddenly realize the landscape looks different than it did hours before. The process has been building for thousands of years as ice continues to form at the poles, locking away water that once flowed freely through the global ocean system. Each winter, more ice forms than melts the following summer. Each year, a little more water is removed from the great circulation system that has maintained these warm, shallow seas for millions of years. But unlike the dramatic glaciations that will characterize later periods of Earth's history, this ice formation happens with geological gentleness. The ice sheets that slowly grow at the poles are not the massive, grinding glaciers that will one day scour continents, but rather more modest accumulations that build up gradually over tens of thousands of years. Think of them as Earth's first tentative experiment with ice ages, a gentle rehearsal for the more dramatic performances that will come much later in geological history. As water continues to be locked away in polar ice, the global sea level begins its slow, steady descent. The change is measured in millimeters per year, then centimeters per decade, then meters per century. For the marine creatures that call these seas home, the change is so gradual that each generation experiences water levels that are virtually identical to those their parents knew. Yet over the span of thousands of years, the cumulative effect is profound and unmistakable. The shallow epicontinental seas that have covered vast areas of the ancient continents for millions of years begin to show their first signs of retreat from the land. These seas, which have been like warm blankets draped over much of the world's landmasses, start to pull back toward the deeper ocean basins, revealing land that hasn't seen sunlight for geological ages. The process is as gentle as water slowly draining from a bathtub, but the scale is continental. Picture the shorelines of these ancient seas as they begin their slow retreat. Where once waves lapped against distant shores, the water edge gradually moves backward, exposing vast expanses of seafloor that have been accumulating sediments for millions of years. These newly exposed areas are like pages from an ancient book, written in layers of limestone and shale that tell the story of the abundant life that has flourished in these warm waters throughout the Ordovician period. The exposed seafloors are initially barren and lifeless, covered with the fine sediments and fossil remains of countless marine organisms that have lived and died in these waters over vast periods of time. The surfaces are soft and muddy, marked by the burrows and trails of creatures that once moved through this underwater landscape when it lay beneath hundreds of feet of warm, life-giving water. Now, these ancient traces of biological activity are exposed to air and sunlight for the first time in their existence. But the retreat of the seas is not uniform or sudden. Instead, it happens in a complex pattern of advances and retreats, like a conversation between land and sea that unfolds over thousands of years. Some areas are exposed gradually and permanently, while others experience cycles of exposure and reflooding as sea levels fluctuate with the seasonal growth and melting of polar ice. This creates a constantly shifting mosaic of marine and terrestrial environments that provides opportunities for life to experiment with new forms and strategies. The marine communities that have thrived in these shallow seas respond to the retreating waters with the same patience and adaptability they've shown throughout the period of gradual cooling. Rather than experiencing catastrophic habitat loss, most communities simply migrate toward deeper water as their traditional homes are slowly exposed. It's like watching a vast, slow-motion evacuation, but one that happens with such geological patience that it feels more like a gentle migration than a desperate retreat. The crinoid forests that have created underwater cathedrals across these shallow seas begin to relocate to deeper waters as their traditional habitats slowly emerge above sea level. These sea lilies, with their flexible stems and efficient feeding apparatus, prove remarkably adaptable to the changing depth conditions. Some species that once thrived in water just a few feet deep successfully establish new communities in waters tens of feet deeper, adjusting their feeding strategies and growth patterns to cope with the different light and current conditions they encounter in their new homes. The process of community relocation happens with fascinating coordination. As the water retreats, the various species that have lived together in complex interdependent relationships don't simply scatter randomly toward deeper water. Instead, they tend to migrate together, maintaining the ecological partnerships that have made their communities successful. Predators follow their prey species toward deeper water. Filter feeders relocate to areas where their symbiotic partners can also thrive. Reef builders establish new construction projects in depths that can support their architectural requirements. The brachiopod beds that have carpeted vast areas of shallow seafloor also begin their migration toward deeper waters. These filter-feeding organisms, which have specialized in extracting nutrition from the nutrient-rich waters of the shallow seas, face the challenge of adapting to the different water chemistry and flow patterns they encounter in deeper environments. Some species prove remarkably adaptable, modifying their feeding apparatus and shell architecture to thrive in their new homes. Others find niches in the transitional zones where retreating seas create new types of coastal environments. Perhaps most remarkably, some brachiopod communities begin to exploit the opportunities created by fluctuating water levels in areas where the sea retreat is not permanent. These dynamic environments, where water levels rise and fall with seasonal and longer-term cycles, create new ecological niches that some species find particularly attractive. They develop strategies for surviving temporary exposure to air and taking advantage of the concentrated nutrients that result from periodic drying and reflooding of their habitats. The trilobite communities that have dominated the seafloors of these ancient seas also demonstrate remarkable adaptability to the changing conditions created by sea level retreat. Many species successfully transition to deeper water environments, modifying their feeding and behavioral strategies to cope with the different sediment types and prey communities they encounter. Others discover opportunities in the dynamic coastal environments created by fluctuating sea levels, developing tolerance for variable salinity and temperature conditions. Some trilobite lineages begin to experiment with adaptations that allow them to exploit the newly exposed coastal environments. While these ancient arthropods never fully transition to terrestrial life, some species develop enhanced abilities to survive in very shallow water and even brief exposure to air. They become pioneers of the intertidal environments that are created as sea levels fluctuate in the coastal zones. The great nautiloids that have been apex predators in these ancient seas face perhaps the greatest challenges as their hunting territories shrink with the retreating waters. These sophisticated predators, with their elaborate shells and complex behavior patterns, respond to changing conditions by modifying their hunting strategies and expanding their depth ranges. Some species that once hunted primarily in shallow waters develop the ability to hunt effectively in deeper environments, adjusting their buoyancy control and sensory systems to cope with different pressure and light conditions. The retreat of the seas also creates new opportunities for some nautiloid species as the concentration of marine life in smaller areas increases prey density in the remaining deep-water habitats. Some lineages become more specialized for hunting in these concentrated prey communities, developing new predatory strategies that take advantage of the increased competition and interaction among potential prey species. As the shallow seas continue their slow retreat, they leave behind a legacy that will influence the development of life on Earth for millions of years to come. The newly exposed land areas, covered with marine sediments rich in calcium carbonate and other minerals, create new opportunities for the primitive land plants that are just beginning to colonize terrestrial environments during this period. These early land plants, still simple and small compared to the massive marine forests of the ancient seas, begin to take advantage of the mineral-rich soils left behind by the retreating waters. The calcium carbonate that once formed the shells and skeletons of countless marine organisms becomes available as a nutrient source for terrestrial vegetation. The organic matter trapped in marine sediments provides rich fertilizer for plant communities that are learning to live in the harsh conditions of the land surface. The interaction between retreating seas and expanding terrestrial vegetation begins to create new feedback loops that will influence global climate and ocean chemistry for geological ages to come. As plants colonize the newly exposed land areas, they begin to weather rocks and sediments in ways that alter the chemical composition of water that flows from the land back to the seas. They also begin to remove carbon dioxide from the atmosphere through photosynthesis, contributing to the cooling trends that are driving the sea level retreat in the first place. The retreat of the seas also affects the global circulation patterns that have maintained warm, stable conditions throughout the Ordovician period. As shallow seas disappear, the ocean circulation system loses some of its most important pathways for distributing heat and nutrients around the globe. The loss of these circulation routes contributes to further cooling and creates new patterns of ocean flow that will characterize the post-Ordovician world. The deep ocean basins, which receive the water that drains from the disappearing shallow seas, begin to experience conditions they haven't known for millions of years. The influx of water from the retreating epicontinental seas carries with it different chemical signatures and temperature characteristics that begin to alter the deep ocean environment. Some deep water communities find these new conditions challenging, while others discover opportunities in the changing chemistry and circulation patterns. The coastal environments that are created as the seas retreat become laboratories for evolutionary experimentation. The fluctuating water levels, variable salinity conditions, and dynamic sediment patterns create environmental pressures that drive rapid evolutionary change in the organisms that learn to exploit these new habitats. Some of the most important evolutionary innovations of the late Ordovician period emerge from communities that learn to thrive in these dynamic coastal environments. The retreat of the seas also begins to affect global weather patterns as the relationship between land and ocean changes across the planet. The loss of shallow seas, which have acted like vast thermal reservoirs helping to moderate global climate, contributes to increasing seasonality and regional climate variation. Areas that once enjoyed the moderating influence of nearby shallow seas begin to experience more extreme temperature variations and new patterns of precipitation. As you float in these ancient waters, still warm and life-giving despite all the changes they've undergone, you're witnessing one of the most profound geographical transformations in Earth's history. The seas that stretch around you in every direction are no longer the vast, continent-covering waters they once were. They're becoming more concentrated, deeper, and more chemically complex as they're forced into smaller spaces by the growing polar ice sheets and the emergence of new land areas. Yet, even as these waters retreat, they maintain their essential character as nurseries for life and laboratories for evolution. The marine communities that have called these seas home for millions of years don't simply disappear as their habitat shrinks. Instead, they compress into the remaining deep water areas, creating some of the most densely populated and diverse marine ecosystems in Earth's history. The intensity of life in these remaining seas is remarkable, with species packed into available habitats with an efficiency that speaks to life's extraordinary ability to adapt to changing circumstances. The Great Retreat continues with geological patience, reshaping coastlines and creating new landscapes at a pace that allows life to adjust and adapt rather than simply being overwhelmed by change. It's a masterpiece of gradual transformation, showing how even the most fundamental changes to our planet's geography can unfold in ways that preserve continuity while enabling new forms of abundance and beauty to emerge. As the ancient seas slowly give up their hold on the land, they're not dying but transforming, concentrating their life-giving properties into smaller but more intense spaces, creating conditions that will support new experiments in evolution and new forms of marine abundance. The retreat is not an ending, but a transformation. Not a loss, but a reorganization of life's possibilities on a planet that's learning new ways to support the ancient miracle of living systems. There's something deeply peaceful about watching communities adapt to change when that change unfolds slowly enough for wisdom to develop, for new relationships to form, for innovative solutions to emerge from the patient experimentation of countless generations. As you float in these ancient waters, now deeper and more concentrated than they were just a few thousand years ago, you're about to witness one of evolution's most elegant demonstrations of community resilience. The way entire ecosystems can reorganize themselves in response to changing conditions, maintaining their essential functions while discovering new forms of abundance and beauty. The marine communities that have called these seas home for millions of years are now living in a world that's becoming fundamentally different from anything their ancestors knew. The vast, shallow epicontinental seas that once stretched across continents have given way to deeper, more concentrated bodies of water. The warm, stable conditions that supported unprecedented biological diversity have been replaced by more variable temperatures and different chemical compositions. Yet rather than simply declining or disappearing, these ancient communities are demonstrating life's remarkable ability to reinvent itself while preserving the essential relationships that make ecosystem function possible. Think of what's happening as similar to the way a large, sprawling family might adapt when they're asked to move from a spacious house into smaller quarters. Initially, there might be some crowding and confusion as everyone adjusts to the new space. But gradually, family members would find new ways to share resources, develop more efficient routines, and perhaps discover that the closer quarters actually create opportunities for deeper relationships and more creative forms of cooperation. This is precisely what's happening in these ancient seas as marine communities adapt to their new, more concentrated living spaces. The great coral reefs that have created underwater cities across the shallow seas face perhaps the most complex challenges as they adapt to deeper water conditions. These reef communities, built up over millions of years through the collaborative efforts of countless organisms, cannot simply pack up and move to new locations. Instead, they must undergo a fundamental transformation, developing new architectural strategies and new forms of cooperation that allow them to thrive in the different conditions they encounter in deeper water. The coral-like organisms that form the structural foundation of these reefs begin to experiment with new growth patterns that are better suited to the lower light levels and different current patterns they encounter in deeper water. Some species develop more branching, open structures that can capture more of the available light and filter nutrients more efficiently from the slower-moving waters of the deeper seas. Others become more compact and dome-shaped, creating more stable structures that can better withstand the different flow patterns and sediment conditions they encounter in their new environments. Perhaps most remarkably, these reef communities begin to develop new forms of cooperation that allow them to make more efficient use of the resources available in their deeper water homes. Organisms that once competed for the same nutrients begin to specialize in processing different types of food particles, creating more efficient use of the marine snow that drifts down from the surface waters. Species that once occupied similar ecological niches begin to partition their habitat more finely, allowing more diverse communities to coexist in smaller spaces. The bryozoans, those tiny colonial animals that create elaborate reef-like structures, prove particularly adaptable to the changing conditions. These organisms, which build their colonies through the coordinated efforts of thousands of individual animals, begin to construct their communities with new architectural principles that are better suited to deeper water conditions. Some colonies become more three-dimensional, creating complex maze-like structures that provide more surface area for filter feeding in the nutrient-rich but slower-moving waters of the deeper seas. Other bryozoan communities begin to experiment with more flexible construction techniques, building colonies that can bend and sway with the different current patterns they encounter in deeper water. Still, others develop more robust attachment systems that allow them to colonize the rocky surfaces and hard substrates that become more common as they move away from the soft sediments of the former shallow seas. The filter-feeding communities that have dominated the seafloors of the ancient seas also undergo remarkable transformations as they adapt to their new environments. The brachiopods, which have specialized in extracting nutrition from the water column, face the challenge of maintaining their feeding efficiency in water that moves differently and carries different types of suspended particles than the shallow seas they once knew. Some brachiopod species respond to these challenges by developing more sophisticated filtering mechanisms that can extract nutrition more efficiently from the different types of marine snow they encounter in deeper water. They modify the internal structure of their shells to create more complex water flow patterns that allow them to capture smaller particles and process nutrients more thoroughly. Others begin to experiment with different positioning strategies, attaching themselves to elevated surfaces or developing more flexible stalks that allow them to position their feeding apparatus in optimal current flows. Perhaps most interesting of all, some brachiopod communities begin to develop new forms of cooperative feeding that allow them to process nutrients more efficiently than individual organisms could manage alone. Dense beds of brachiopods begin to coordinate their feeding activities, creating complex current patterns that concentrate nutrients and make them available to the entire community. It's like watching the development of a primitive form of agricultural cooperation, where the activities of each individual benefit the productivity of the whole community. The crinoid forests that have created some of the most spectacular underwater landscapes in these ancient seas also demonstrate remarkable adaptability as they transition to deeper water environments. These sea lilies, with their feathery feeding arms and flexible stems, face the challenge of maintaining their feeding efficiency in lower light conditions and different current patterns than they've known for millions of years. Some crinoid species respond by developing more elaborate and efficient feeding apparatus, growing longer arms with more complex branching patterns that can capture food particles more effectively in the gentler currents of deeper water. Others modify their growth strategies, developing shorter, more robust stems that are better suited to the different flow patterns they encounter, or creating more flexible attachment systems that allow them to colonize new types of substrates. The coordination between different crinoid species within these transitioning forests is particularly fascinating to observe. Species that once competed for the same feeding zones begin to specialize at different heights within the water column, creating more efficient use of the available current flows and food resources. Some species begin to grow taller to capture food particles before they settle to lower levels, while others specialize in processing the material that filters down from their neighbors above. This vertical specialization creates underwater forests that are even more complex and efficient than their shallow water predecessors. The new crinoid communities that develop in deeper waters often support more species diversity than the original forests, as the more three-dimensional structure and specialized feeding strategies create more ecological niches for different organisms to exploit. The mobile communities that move through these transitioning underwater landscapes also demonstrate remarkable adaptive flexibility. The trilobites that have dominated seafloor ecosystems for millions of years prove particularly successful at adapting to the changing conditions, developing new feeding strategies and behavioral patterns that allow them to thrive in the more concentrated and competitive environments of the deeper seas. Some trilobite species become more specialized in their feeding habits, developing enhanced sensory systems that allow them to locate and exploit specific types of food resources that are abundant in their new environments. Others become more generalized, developing the ability to switch between different feeding strategies as opportunities arise. Still others begin to exploit the new ecological niches created by the more complex three-dimensional structure of the deeper water communities. The predatory trilobites that hunt other small organisms also adapt their strategies to the new conditions they encounter. The more concentrated prey communities in the deeper waters create opportunities for more efficient hunting, but they also create more competition among predators. Some species respond by becoming more specialized hunters, developing enhanced abilities to catch specific types of prey. Others become more social, developing rudimentary forms of cooperative hunting that allow them to take advantage of the dense prey communities more effectively. The great nautiloids that cruise through these ancient waters like living submarines face perhaps the most significant adjustments as they adapt to hunting in the more concentrated and competitive environments of the deeper seas. These sophisticated predators, with their complex eyes and jet propulsion systems, must develop new hunting strategies that allow them to compete effectively in ecosystems where prey is both more abundant and more heavily hunted than in the spacious shallow seas they once knew. Some nautiloid species respond by becoming more specialized in their hunting techniques, developing enhanced abilities to catch specific types of prey that are abundant in the new environments. They modify their shell shapes and propulsion systems to become more efficient at particular types of hunting, whether that's pursuing fast-moving prey through open water or hunting sedentary organisms among the complex structures of the transitioning reef communities. Others become more opportunistic, developing the behavioral flexibility to switch between different hunting strategies as conditions change. These adaptable hunters learn to exploit the seasonal cycles and daily rhythms of their new environments, timing their hunting activities to take advantage of periods when prey is most vulnerable or abundant. Perhaps most remarkably, some nautiloid species begin to show what appears to be cultural transmission of hunting techniques, with successful hunting strategies spreading through populations faster than would be possible through genetic inheritance alone. While these ancient creatures certainly don't possess the complex intelligence of modern cephalopods, they do demonstrate behavioral flexibility that allows them to learn from experience and modify their activities based on changing conditions. The planktonic communities that drift through the surface waters above these transitioning seafloor ecosystems also undergo significant reorganization as they adapt to the changing physical and chemical conditions of the ancient seas. The different temperature and circulation patterns created by the deeper, more concentrated ocean basins provide new opportunities for planktonic organisms while also creating new challenges. New planktonic species continue to evolve that are better adapted to the changing conditions, while existing species modify their distribution patterns and seasonal cycles to take advantage of new nutrient cycling patterns. Some planktonic communities become more stratified, with different species specializing at different depths within the water column to take advantage of the more complex vertical structure of the deeper ocean basins. The changes in planktonic communities create ripple effects throughout the entire marine ecosystem as the composition and timing of marine snow changes in response to new planktonic species and behaviors. Filter feeding communities must adapt their feeding strategies to process different types of organic matter, while predatory species must adjust their hunting patterns to follow the changing distributions of their prey. The seasonal cycles that govern life in these ancient seas also begin to show new patterns as the marine communities adapt to the different physical conditions of their more concentrated habitats. The thermal properties of deeper water create different seasonal temperature variations, while the changing circulation patterns alter the timing and intensity of nutrient cycling. Marine communities adapt to these new seasonal patterns by modifying their reproductive cycles, feeding behaviors, and migration patterns. Some species begin to reproduce at different times of the year to take advantage of new seasonal patterns of food abundance. Others modify their metabolic rates to better cope with the different seasonal temperature variations they encounter in deeper water. Still, others develop new forms of seasonal behavior, such as vertical migrations that allow them to take advantage of different conditions at different depths throughout the year. The chemical cycling within these transitioning ecosystems also begins to show new patterns as organisms modify their metabolic processes and waste production in response to the different conditions they encounter. The more concentrated nature of the deeper water communities creates more intense recycling of nutrients and dissolved chemicals, leading to more complex chemical gradients and more sophisticated biochemical relationships between different species. Some organisms begin to specialize in processing specific types of chemical waste produced by their neighbors, creating more efficient nutrient cycling within the community. Others develop new biochemical pathways that allow them to take advantage of the different chemical conditions created by the more intense biological activity in the concentrated deeper water habitats. Throughout all of these transitions, the essential character of these marine communities remains remarkably stable. The fundamental strategies that have made these ecosystems successful, filter feeding, predation, reef building, planktonic photosynthesis, continue to operate even as the specific ways they're implemented undergo continuous modification. It's like watching a symphony orchestra adapt to playing in a different concert hall, maintaining the essential beauty and structure of the music while adjusting their techniques to suit the new acoustic environment. The pace of these community transitions matches the pace of environmental change, creating a harmonious relationship between ecological adaptation and environmental transformation. Each generation of organisms experiences conditions that are only slightly different from those their parents knew, allowing communities to maintain their essential functions while gradually developing new forms of organization and new survival strategies. As you float here among these transitioning communities, surrounded by creatures that are demonstrating life's most sophisticated responses to environmental change, you're witnessing one of evolution's greatest achievements: the ability of complex ecosystems to maintain their stability and productivity even as fundamental conditions undergo profound transformation. The communities around you are not simply surviving change. They're using it as an opportunity to develop new forms of abundance and new types of relationships that will serve as the foundation for the next chapter in life's long and beautiful story. Sometimes the most beautiful transformations happen not when something ends, but when something entirely new begins to emerge from familiar elements arranged in ways that have never been tried before. As you drift peacefully in these ancient waters, now deeper and more concentrated than they were in the early days of our journey together, you're about to witness one of Earth's most gentle revelations: the slow emergence of landscapes that have been hidden beneath warm seas for millions of years, and the patient colonization of these new worlds by life forms that are learning, for the first time, how to exist in the bright, dry realm above the water's surface. The process of land emergence happens with the same geological patience that has characterized all the changes you've witnessed in these ancient seas. Where once waves lapped against distant shores that seemed to mark the eternal boundary between sea and sky, new coastlines are slowly revealing themselves as the retreating waters expose vast expanses of seafloor that have been accumulating sediments and fossil remains for geological ages. These newly emerged lands are like blank canvases waiting for life to begin painting new forms of existence across their virgin surfaces. Picture these emerging landscapes as they first appear above the retreating waters. Vast, flat expanses covered with the fine-grained sediments and limestone deposits that once formed the floor of shallow seas. The surfaces are soft and muddy at first, marked by the fossilized burrows and trails of marine creatures that once called this underwater realm home. In the gentle morning light that touches these surfaces for the first time in millions of years, you can see the delicate patterns left by ancient trilobites, the spiral shells of long-dead nautiloids, the branching forms of crinoid stems that once swayed in underwater currents. The air above these newly exposed lands carries a different quality than the atmosphere above the ancient seas. Drier, touched with the mineral scent of limestone and shale, stirred by breezes that no longer carry the moisture-laden warmth of purely marine air. It's an atmosphere that's learning how to be continental, how to carry the chemical signatures of rock and soil, rather than just the salt and organic richness of the sea. At first, these emerging lands are completely barren of life, as sterile and lifeless as the surface of an alien planet. The transition from underwater to terrestrial environment is so dramatic that no marine organism can survive the change without fundamental adaptations that take many generations to develop. Yet even in their initial barrenness, these new landscapes carry within them the potential for entirely new forms of existence. The mineral composition of these emerged seafloors creates ideal conditions for the development of terrestrial life. The calcium carbonate that once formed the shells and skeletons of countless marine organisms has been broken down and mixed with organic matter to create soils that are rich in nutrients and perfectly balanced for supporting plant growth. The limestone substrates provide excellent drainage while retaining enough moisture to support delicate root systems. It's as if the ancient seas have left behind a gift for the terrestrial life that will eventually colonize these new lands. The first colonizers of these emerging landscapes are not animals, but plants, though even the term plants might be misleading when applied to the simple, primitive organisms that begin to establish themselves in the mineral-rich soils left behind by the retreating seas. These early terrestrial colonizers are small, simple organisms, not much more complex than the algae that drift through the surface waters of the ancient seas, yet they represent one of the most significant evolutionary advances in the history of life on Earth. These pioneering plants face challenges that no living organism has ever encountered before. They must learn to extract water and nutrients from soil rather than directly from surrounding water. They must develop structural support systems that can hold them upright against the pull of gravity without the buoyant support of seawater. They must create protection against the drying effects of air and the intense radiation of direct sunlight. Most challenging of all, they must develop reproductive strategies that work in the dry, variable conditions of the terrestrial environment. The solutions these early plants develop to these challenges happen slowly, through the patient experimentation of countless generations. Some lineages develop more efficient root systems that can extract water and nutrients from soil more effectively. Others evolve waxy coatings that help prevent water loss through their surfaces. Still others begin to experiment with structural tissues that provide support and transportation systems for moving water and nutrients throughout their increasingly complex bodies. The colonization of these emerging lands happens in stages, like the gradual settlement of a new territory by pioneers who prepare the way for those who will follow. The first plants to establish themselves are small and simple, creating thin mats of vegetation that help stabilize the soft soils and begin the process of creating more complex terrestrial ecosystems. As these pioneer communities become established, they create conditions that make it possible for slightly more complex plants to survive and thrive. The interaction between these early terrestrial plants and the mineral-rich soils left behind by the ancient seas creates new forms of chemical weathering that begin to alter the composition of water that flows from the land back to the sea. as plant roots penetrate deeper into the limestone substrates. They release organic acids that dissolve minerals and create new types of dissolved chemicals that eventually make their way back to the marine environment through rivers and streams. This chemical feedback between emerging terrestrial ecosystems and the ancient seas creates one of the first examples of the complex interconnections that will eventually characterize the relationship between land and ocean systems. The plants that colonize the emerging lands don't exist in isolation from the marine ecosystems that still dominate the planet. Instead, they become part of an expanded global ecosystem that includes both terrestrial and marine components. The emergence of these new lands also begins to affect local climate patterns in ways that create new opportunities for both terrestrial and marine life. The newly exposed land masses absorb and reflect solar energy differently than the water they replace, creating new patterns of heating and cooling that generate different wind patterns and precipitation cycles. Some areas that were once uniformly marine begin to develop the beginnings of continental weather patterns, with more variable temperatures and seasonal cycles than the stable marine climate they once knew. These climatic changes, while still subtle compared to the dramatic weather systems that will characterize later geological periods, begin to create new ecological niches that can be exploited by both terrestrial and marine organisms. Coastal environments that experience daily and seasonal fluctuations between marine and terrestrial conditions become laboratories for evolutionary experimentation, where organisms can develop adaptations that allow them to exploit both aquatic and terrestrial resources. Some of the most interesting evolutionary developments during this period occur in these transitional coastal environments, where the boundaries between marine and terrestrial ecosystems are fluid and constantly changing. Organisms that can tolerate variable salinity, periodic drying, and fluctuating temperatures begin to explore the possibilities of existence at the interface between the ancient seas and the emerging lands. The newly exposed lands also begin to affect the global carbon cycle in ways that contribute to the ongoing cooling trends that have been reshaping the ancient seas. As terrestrial plants begin to photosynthesize using atmospheric carbon dioxide, they start to remove this greenhouse gas from the atmosphere more efficiently than purely marine ecosystems could manage. The burial of organic matter in terrestrial soils also begins to sequester carbon in ways that were not possible when all of Earth's biological activity was concentrated in marine environments. As you continue to float in these ancient waters, now surrounded by emerging landscapes that represent entirely new experiments in the possibilities of life on Earth, you're witnessing one of the most profound transitions in our planet's history. The emergence of these new lands doesn't represent the end of the marine world you've been exploring, but rather the beginning of a more complex and diverse global ecosystem that will include both oceanic and terrestrial components. The pace of these changes remains comfortably slow, unfolding over thousands of years in ways that allow both marine and terrestrial life to adapt gradually to the new conditions. There's something deeply peaceful about this patient emergence of new worlds from ancient waters, this gentle expansion of life's possibilities into realms that have never been explored before. The transformation happens with the same geological patience that has characterized all the changes you've witnessed, creating new forms of beauty and abundance without destroying the ancient harmonies that have sustained life in these seas for millions of years. As you drift through these ancient waters, now transformed by millions of years of gentle change, you begin to sense that something fundamental has shifted in the character of the seas around you. The water still holds you in its warm embrace, still supports the abundant life that has made these oceans home for countless generations. But there's a different quality to the marine world now, a sense that these seas have learned new ways of being, developed new rhythms and patterns that speak of a world that has passed through transformation and emerged as something both familiar and entirely new. The seas that cradle you now are deeper and more concentrated than those early tropical waters you first encountered at the beginning of this journey. The vast, shallow epicontinental seas that once covered continents have given way to more defined ocean basins, creating bodies of water that are more three-dimensional, more vertically complex, with distinct layers and zones that support different types of marine communities. It's as if the ocean has gained depth, not just in its physical structure, but in its ecological complexity and sophistication. The marine communities that populate these transformed seas show the results of their long adaptation to changing conditions. The reef communities that once created sprawling underwater cities across shallow seafloors have evolved into more compact, but incredibly diverse ecosystems, where dozens of species cooperate in intricate relationships within smaller spaces. These new reef communities are like underwater metropolises, where efficiency and cooperation have been refined to an art form through thousands of years of gradual adaptation. The filter-feeding communities that carpet the seafloors of these deeper waters have developed feeding strategies of remarkable sophistication, creating complex, three-dimensional structures that process nutrients with an efficiency that their shallow-water ancestors never achieved. The brachiopods and bryozoans that form these communities have learned to work together in ways that maximize the extraction of nutrition from the marine snow that drifts down from the surface waters, creating biological machines of incredible elegance and effectiveness. The planktonic communities that drift through the surface waters above you have also undergone profound changes, developing new species and new relationships that are perfectly adapted to the different temperature and circulation patterns of the transformed seas. These microscopic organisms, invisible individually, but collectively responsible for supporting all marine life, have created new forms of cooperation and specialization that make more efficient use of sunlight and dissolve nutrients than ever before. Perhaps most remarkably, these transformed seas have developed new seasonal rhythms that are more complex and more predictable than the gentle cycles that characterize the early Ordovician oceans. The different thermal properties of the deeper water create seasonal temperature variations that drive new patterns of biological activity, while the more defined circulation patterns create seasonal cycles of nutrient upwelling and plankton blooms that support marine communities with remarkable reliability. These new seasonal patterns create opportunities for marine organisms to develop more sophisticated life strategies, with some species timing their reproduction to coincide with seasonal peaks in food availability, while others develop the ability to migrate vertically through the water column to take advantage of different seasonal conditions at different depths. The result is a marine ecosystem that pulses with seasonal rhythms, more complex and beautiful than anything the ancient seas had known before. The chemical composition of these transformed seas also reflects the changes they've undergone, carrying dissolved minerals and gases that speak of the complex interactions between ocean, atmosphere, and the newly emerged lands. The water around you carries chemical signatures from terrestrial weathering processes, creating new conditions that support different types of marine life, while maintaining the essential life-supporting properties that have made these seas home for countless organisms. As our long journey through these ancient waters draws to its peaceful close, you find yourself floating in seas that have taught you something profound about the nature of change itself. How transformation can unfold with such grace and patience that it enhances rather than destroys, creates rather than eliminates, builds new forms of abundance while honoring the ancient wisdom of the systems that came before. The story you've witnessed in these waters is ultimately a story about time itself. Geological time, evolutionary time, the kind of deep time that allows changes to unfold with such patience that every generation has the opportunity to adapt, to find new solutions, to discover new possibilities within the slowly shifting conditions of their world. This is time measured not in heartbeats or seasons, but in the slow accumulation of limestone, the gradual drift of continents, the patient experimentation of countless generations of organisms learning new ways to thrive. Through all the changes you've witnessed, the cooling waters, the retreating seas, the emergence of new lands, the adaptation of ancient communities to new conditions, there's been a consistent thread of resilience and creativity that speaks to life's most fundamental characteristic: its ability to find ways to flourish even as the conditions that support it undergo profound transformation. The creatures you've encountered on this journey, from the patient trilobites crawling across ancient seafloors to the graceful crinoids swaying in underwater forests, from the sophisticated nautiloids cruising through deep waters to the tiny planktonic organisms that support all marine life, have demonstrated that adaptation is not about struggle or conflict, but about patience, creativity, and the willingness to experiment with new ways of existing in harmony with an ever-changing world. As you float here in these transformed seas, surrounded by the gentle sounds of water and the peaceful rhythms of marine life, you might find that the lessons of these ancient waters begin to influence your own relationship with change and time. The patient approach these creatures have taken to adaptation, accepting change as a natural part of existence, responding to challenges with creativity rather than resistance, finding new forms of abundance even as familiar conditions transform, offers a different way of thinking about the changes and challenges that characterize your own life. The deep time you've experienced on this journey, where changes unfold with geological patience, and every transformation is given the space and time it needs to develop naturally, provides a different perspective on the often frantic pace of modern existence. There's something deeply restful about contemplating time measured in millions of years, changes that unfold across thousands of generations, transformations so gradual they're almost imperceptible, yet ultimately profound in their effects. As you begin to let yourself drift deeper into the peace of these ancient waters, surrounded by creatures that have learned to live in harmony with change, you might find that your own breathing begins to slow to match the patient rhythms of geological time. Your heartbeat might begin to synchronize with the gentle pulse of ancient seas. Your awareness might begin to expand to encompass the vast, slow processes that shape worlds and create conditions for new forms of life to emerge. The ancient seas around you continue their eternal circulation, carrying nutrients and dissolved gases through cycles that connect every drop of water, every grain of sediment, every living organism in patterns of relationship that extend across the entire planet. These connections, invisible but fundamental, remind you that you too are part of these vast cycles, connected to every other living thing through relationships that extend back to the very origins of life in these ancient waters. As you float peacefully in this timeless moment, suspended between the warm surface and the mysterious depths, between the ancient past and the infinite future, you might find that the boundaries between yourself and the gentle waters around you begin to soften. The peace of these ancient seas begins to become your peace. Their patient rhythms begin to become your rhythms. Their deep acceptance of change and transformation begins to become your own approach to the flowing nature of existence. Let yourself sink deeper into this ancient peace, this geological patience, this evolutionary wisdom that has sustained life through every transformation our planet has undergone. Allow the gentle currents of these ancient waters to carry away any urgency or anxiety, any need to rush or struggle against the natural pace of change and growth in your own life. The story of these ancient seas will continue long after our journey together ends, their waters continuing to flow, their creatures continuing to adapt and evolve, their patient processes continuing to create new forms of abundance and beauty. And in some way, you will always be part of this story, connected to these ancient waters through the water in your own body, the minerals in your bones, the oxygen you breathe that was once dissolved in these primordial seas. Rest now in the gentle embrace of these ancient waters, surrounded by the peaceful sounds of life that has learned to flourish in harmony with change, supported by currents that have been flowing for hundreds of millions of years and will continue flowing for hundreds of millions of years to come. Let the deep time of these ancient seas become your time, their patience become your patience, their peace become your peace, as you drift gently toward the shores of sleep, carried by waters that connect you to the very origins of life itself. The ancient seas hold you safely now, as they have held countless creatures throughout the long history of life on Earth, offering the same gentle support, the same patient acceptance, the same unconditional embrace that has sustained life through every transformation, every challenge, every beautiful change that has shaped our world. Rest peacefully in these timeless waters, and let their ancient wisdom guide you gently into dreams as deep and peaceful as the geological time that flows through every moment of existence.